The ideas that we've had so far have been based around disks, basically, or disks with a hole in them, as in the Warscher method. Sometimes there's an alternative method that you can use that will cause the calculations to be a lot easier. To illustrate this, I want to do a problem with the disk-Warscher method and then start talking about the new idea, and we'll see that in this particular case anyway, that it's a lot easier. I want to look at the region of the first quadrant below the graph of y equal 4x minus x squared, and I want to think about revolving this about the vertical line where x is 5. Since the axis of rotation is vertical, if I want to use disk or disk-like methods, it's the range of y values that will get subdivided. Thinking of the typical pieces that we will revolve around this vertical line, I'll draw a few of them in. I'll have a collection of Warschers with their axis of symmetry, the vertical line x equal 5. I'm going to have to figure out the big radius and the small radius for each one of these. Selecting one of the horizontal strips, I'm not interested in all points that are between those two dotted lines, only these points. For a given y value, typically there'll be two x values on the parabola to go with it. The inside radius is the horizontal distance from x equal 5 to as close to the axis of rotation as I can get. The small radius is 5 minus the x-coordinate of the right-hand end of that horizontal strip. On the other hand, the large radius is the distance from x equal 5 to as far away as I can get from the axis of rotation within that strip. The big radius is 5 minus the x-coordinate of the left-hand end of the horizontal strip. To proceed, I'll think of having a y value. I'm going to need to figure out the ends of that horizontal strip. Then I'll subtract the bigger x-coordinate from 5 to get the small radius. I'll subtract the smaller x-coordinate away from 5 to get the big radius. Given a y number, I need to know the x numbers on this parabola that go with it. I need to solve this equation for x in terms of y. Add x squared to both sides, subtract 4x, and I find out that x squared minus 4x plus y must be 0. I regard y as given number in the y range. I have to figure out what the x is. I'm going to regard y as a known number for this. This is a quadratic equation, then for x, there's a variety of ways that you could solve this. Because the arithmetic isn't very difficult, I'll just complete the square. Move the constant term over to the other side. I've got x squared minus 4x remaining on the left. Half of 4 is 2. I wish it had 2 squared added in. Supplying the 2 squared turns the left-hand side into a perfect square, the square of x minus 2. X minus 2 is either radical 4 minus y, or the negative of that quantity. X is 2 plus or minus square root of 4 minus y. The larger of the two is the one that goes with the plus sign. The smaller goes with the negative sign. As previously mentioned, in this situation, the small radius is 5 minus the right end x-coordinate of the horizontal strip. Well, the big radius is 5 minus the x-coordinate of the left end. In the recipe for the volume, I need to have the big radius squared minus the small radius squared. Each of these is easy to write out using the a plus b quantity squared idea and the a minus b quantity squared. In the subtraction, 3 squared cancels out. The terms at the end, the 4 minus y, cancels out, leaving 6 radical 4 minus y. Minus minus is plus, so that's going to give 12 times the square root of 4 minus y. Since I'm thinking of evaluating this at some representative y number called Cj, this will be 12 times the square root of 4 minus Cj when I begin setting the integral up. Writing out the recipe, pi times big radius squared minus small radius squared worked out to be 12 radical 4 minus Cj. The perpendicular height is delta y number j. Adding up the contributions and taking the limit, as all of the delta y's tend to 0, this turns into an integral. From the graph, the y values go from y equals 0 to y equals 4, so those are the limits of integration. Using the Disk-Warscher method, we have now set up the integral required to figure out the volume of the indicated solid. All that remains is to evaluate the integral. I can go on and take the constant factor out. Usually when I work these problems, I go off to the side, figure out the antiderivative, usually with some sort of substitution or other trick, and then evaluate the integral in terms of the y variable. This time, I think I'll do a substitution, and instead of doing what I just said, I'll just deal with the integral in terms of the new variable for variety. Letting u equal 4 minus y, the derivative of u with respect to y is negative 1. du is negative 1 times dy. dy is the negative of du, negative 1 times du. And as for the limits of integration, when y is 0, u will be 4 minus 0, which is 4. And in y is 4, u is 4 minus 4, which is 0. The integral that I have to calculate is 12 pi times the integral from 4 to 0 of the square root of u times negative 1 du. This looks kind of weird because the number upstairs is the smaller one of the two, but everything will work out all right because of the factor of negative 1. Taking the constant factors out front, square root of u is u to the 1/2 power, and antiderivative of that with respect to u will involve u to the 3/2 power, and we have to have a factor that is the reciprocal of the new power, the 1 over n plus 1 business. 1 over 3/2 is 2/3. You can cancel a 3 out between the 12 upstairs and the 3 downstairs, leaving 4 times pi times 2 times negative 1 as the constant factor, negative 8 pi, multiplied by 0 to the 3/2 power, which is 0, minus 4 to the 3/2 power, which we still have to figure out. So after doing the arithmetic, it turns out that the volume of the indicated solid is 64 pi cubic units of volume, whatever the units are. The hard part here really was setting the integral up. Having to locate the big radius and the small radius made this sort of painful. In the disk and its variation, Warscher method, we have objects with circular cross sections, and we slice them up into smaller pieces with the same cross section, or at least the same type, and it is the perpendicular heights that tend to zero at the end of the calculation. In the new method, which is going to be called the shell method, I think of taking my solid and splitting it up into concentric hollow shells instead. To figure out what to do, we need to figure out the volume of one of these shells and what's going to end up going to zero when we turn this into an integral. I'm going to think of taking one of these shells and describing it with three numbers. Firstly, there'll be the radius of the shell. I'm going to travel from the axis of symmetry, which will turn out to be the axis of rotation in our problem, out to roughly where the material of the shell is. I'll call that distance the radius. The dimension that's vertical in my picture, I'll just call the height. The only other thing that has any bearing on how much material is in the shell is how thick the wall of the shell is. I'll call that the shell wall thickness. The argument that I'm about to do is a heuristic approximate argument, but it's easy to understand and does produce the correct answer. I'm going to imagine taking an X-Acto knife and cutting down one side of the shell. And then I'm going to flatten the shell out. By doing this, I don't change the height, I don't change the shell wall thickness, but I do change the cross-section from a circle into a line type thing. The distance around a circle is 2 pi times its radius. So when I do this, I get the following picture. This is roughly a rectangular box. One dimension is 2 times the radius of the shell, another is the height of the shell, and the third dimension is the shell wall thickness. Purists will object and say that the distance around on the inside is less than the distance around the outside. If the shell wall thickness hung around as an actual number, that would be a serious concern. But what we're going to do is we're going to let the shell wall thicknesses tend to zero, so in the end, it doesn't matter. So I'll roughly treat this as though it were a rectangular box. The volume of a rectangular box is length times width times height. So instead of using the recipe for disks, which was pi times radius squared times perpendicular height, or for Warschers, which was pi multiplied by big radius squared minus small radius squared times perpendicular height, if I'm going to use shells, the recipe is 2 pi times the radius times the height times the shell wall thickness. I want to return to the problem that we were looking at using the Warscher method a while back. If we were to divide the y range up into smaller subintervals, because of the way we're rotating here, we would get Warschers again. So let's not do that. Let's split up the x range instead. If I think of taking the points in the region that I'm going to revolve that go with one particular subinterval, If I take that vertical strip and revolve it around the vertical line where x is 5, I don't get a disk or washer, I get a shell instead. In order to write down the formula for the volume of such a shell, I need to identify the radius of the shell, the height of the shell, and the shell wall thickness will just be delta x number j. The distance that I've indicated, the x-coordinate that I'm going to use to describe the vertical strip, x equals cj, is how far out from the y-axis I am. But I'm not revolving around the y-axis. I'm revolving around the vertical line where x is 5. The actual distance of my vertical strip from the axis of rotation is not c number j, it's the horizontal distance between x equals 5 and x equals c number j. The vertical strip, in this particular case, goes all the way from y equals 0 up to the y-coordinate on the graph of the parabola that goes with my representative x value, cj. Since y is 4x minus x squared, the height of my shell is just going to be that quantity evaluated at x equals cj. And since we've already decided that the shell wall thickness is going to be delta x number j, we know everything we need to know to write our recipe down. The volume that goes with shell number j is approximately 2 pi times 5 minus cj times 4cj minus cj squared times delta x number j. As usual, we're going to add up all of these things and take the limit. In this, the variable is x and the cj are representative x numbers. Remembering from the picture, the x for the region that we're interested in can be anything as small as 0 or anything as big as 4. Those are the limits of integration. This is considerably easier to obtain, the integral, than what went on with the Warscher method. 2 pi is a constant factor. I can pull it out in front of the integral. I'll also multiply out 5 minus x multiplied by 4x minus x squared. In contrast with whatever went on with the Warscher method, I just have to integrate a polynomial. There's no square root, there is no substitution needed. The remaining antiderivative is easy to get. 10x squared minus 3x cubed plus 1/4 x to the 4th. When I evaluate those at 0, the antiderivative is 0. Only the x equals 4 contributes anything. Doing the arithmetic, this turns out to be 2 times pi times 32, which is 64 pi, which is the same answer we got with the Warscher method, but this was a lot easier. Sometimes one of these two methods turns out to be much easier than the other. In this problem, I'm going to take the region in quadrant 1, bounded by the y-axis, the line y equal x, and the line y equal 2 minus x, and I'm going to revolve that around the vertical line x equals 6. If I wanted to do this with the Warscher method, I would have a big problem. The two lines cross each other, so for some of the y values, the thing that's going to determine the small radius would be the downward sloping straight line. But if the y-coordinate was small enough, below this intersection point, the thing that would determine the small radius would be determined by y equal x. I'd have to split this up into two problems. I'd have to split it up into y going from 0 up to whatever the y coordinate of this intersection point is, and then I would also separately have to think about y equal whatever this number is up to y equal 2. I would have to do two different intervals. If I do the shell method, though, it's not so bad. I have to think, am I going to revolve vertical things or horizontal things? If I revolve horizontal, I'll be in the disk washer method. Therefore, I want to revolve vertical things instead. The smallest x number in my region is 0. That's when you're on the y-axis. The biggest x number is going to be the x-coordinate of the intersection point. So I need to find an x number so that when I feed it into y equal x, and also feed it into y equals 2 minus x, that I get the same answer. That's going to require that x and 2 minus x be the same number. If x is 2 minus x, if you add x to both sides, you find out that 2x has to be 2, and then obviously that tells you that x is 1. The limits of integration with respect to the x variable are x equals 0 and x equals 1. Looking at a typical strip, the x-coordinate will be some number Cj that could be as small as 0 or as big as 1. That's the distance from the y-axis, but we're not revolving around the y-axis. We're revolving around x equals 6. So the horizontal distance of the vertical strip from the axis of rotation is 6 minus the representative x-coordinate, 6 minus Cj. We now know the radius of the shell. I also need to know the vertical height of the shell. I'll think of using the y-axis as a ruler. To get the vertical height, I'll take the larger y-coordinate and subtract the smaller one. The graph that's above is y equals 2 minus x. If I evaluate that at x equals Cj, I'll have 2 minus Cj. The bottom of the strip is located on the line y equal x. If x is equal to Cj, y will be Cj. The vertical height is going to be the larger y-coordinate, the upper one, minus the smaller one, the lower one. The vertical height of the shell is going to be 2 minus 2 times Cj. We know the radius, we know the height, the shell wall thickness will be delta x number j. We're all set. I've got to have 2 pi times the radius, times the height, times the shell wall thickness, add up all such contributions, and take the limit as all of the delta xj's tend to 0. As usual, this is the definition of an integral. Leaving all the usual talking out, this is the integral that I have to evaluate. Just like one of the previous ones, this is just a polynomial. 2 pi is a constant factor, so it can be brought out front. After doing the FOIL method on the integrand, the thing we're integrating, I find out that I need to evaluate 2 pi times integral from 0 to 1 of 2x squared minus 14x plus 12. This is easy to find an antiderivative of. At x equals 0, The antiderivative is 0, so I'll disregard that. At x equal 1, all powers of x are 1, so this isn't very complicated. Negative 7 plus 12 is 5. 5 is 15 over 3. 15 over 3 plus 2 over 3 is 17 over 3. Multiply that by 2 times pi, and you end up with 34 times pi over 3 as the volume of the indicated shape. Not to belabor the point, but we've already figured out the formula for the volume of a right circular cone using the disk/Warscher method. Let's see how complicated it is to figure out the same thing using the shell method. So we'll still have this triangle in the first quadrant, bounded by the x-axis, the y-axis, and the downward sloping line, y equal negative h over rx plus h, which we had previously figured out. If I were to split the range of y numbers up into smaller bits, I would be generating disks. We would be doing what we've done before. So instead, we'll chop the x range up. The smallest relevant x value is 0. The biggest relevant x value is r. These are going to be the limits of integration. To think about a shell, I'll think about one of these subdivisions in the x direction. I'll call the width of the one I'm thinking about delta x number j. I'll pick a representative x value, x equals cj within it. The shell wall thickness is going to be delta x number j, and all we have to do is to correctly identify the radius and the height, and we'll be all set. As always, the radius is the distance of my strip from the axis of rotation. In this case, the axis of rotation actually is the y-axis. The distance of my strip from the axis of rotation is its x-coordinate. The radius is going to be c number j. The height of that shell is going to be a number that goes from y equals 0 up to the y-coordinate on this graph that corresponds to x equals cj. The height of shell number j is going to be negative h over r multiplied by cj plus h. We know the radius, we know the height, we know the shell wall thickness, and we know the range of x numbers that are relevant to the problem. 2 pi times the radius times the height times the shell wall thickness. By this stage, everyone knows what's going to happen. We're going to add up all those contributions and take the limit as all of the delta x's tend to 0. This will turn into an integral. The delta xj's become dx, the cj's become x, and the limits of integration, since x is the variable, will be 0 to r. Then, as usual, pull the constant factor of 2 pi out, and we'll have to do a little bit of rearranging. Keeping in mind that capital H and capital R are just constants, an antiderivative is easy to get. When x is 0, the antiderivative is 0, so I only have to write down the first part where the x is equal to r. If you'll notice, both terms inside the bracket have a factor of h, also a factor of r squared, so we can factor that out. So after we do all the arithmetic, we end up with the volume of the right circular cone being 1/3 pi r squared h, which is as it should be. Hopefully this makes the procedural differences between the disk washer method and the shell method clear enough. I hope everyone's having a good day. I'll talk to you again soon.